Welcome to this explainer. Today we're diving into a truly fascinating and honestly critical advancement in materials science straight from the IMRC 2026 conference. We are talking about the green synthesis of carbon quantum dots specifically engineered for optoelectronics. Let's get right into it.
So, this research, which was a major highlight at the International Materials Research Congress, does something absolutely crucial. It bridges the gap between high-tech optoelectronic applications and truly sustainable materials synthesis. It's basically about getting all those advanced properties we desperately need in modern tech, but without the heavy environmental cost we've historically had to pay.
Okay, here's our roadmap. We'll start with an introduction to CQDs, then look at the green experimental development. After that, we'll dive into the structural evolution using FTIR, check out the optical properties with UV vis and PL, examine the STEM particle morphology, and finally, wrap up with conclusions and applications.
Section 1. Introduction to CQDs.
Now you might be wondering, what exactly are carbon quantum dots, or CQDs? Well, they are incredibly promising fluorescent nanomaterials. Think of them as tiny, highly stable carbon particles that literally glow. They're super valued for their tunable optical properties, amazing photostability, and low toxicity. But here's the catch. Traditional synthesis heavily relies on hazardous chemicals and complex processing, so there is an urgent, undeniable need for a completely green alternative.
Section 2. Green experimental development.
To tackle that environmental challenge head-on, the researchers engineered a completely green, low-cost hydrothermal synthesis route. And the ingredients? They're remarkably simple. We're talking about commercial refined sugar, good old sucrose, and tri-distilled water. That's it. They mix these into an aqueous solution, pop it into an autoclave, and after cooling and centrifugation, out comes this stable, transparent brown CQD dispersion. It honestly looks a bit like dissolved caramel. Absolutely zero hazardous solvents and no toxic byproducts.
To really figure out how this green process ticks, the experimental matrix isolated the impact of two main variables: hydrothermal temperature and reaction time. They tested a temperature range from 140 all the way up to 190 degrees Celsius, and reaction times spanning from a quick 12 hours up to a massive 64 hours. And throughout this entire matrix, the solvent stayed pure water and the precursor stayed sucrose. Section 3. Structural evolution, specifically looking at FTIR.
Now this is where it gets really interesting. These FTIR spectra act essentially like a molecular fingerprint scanner. We can visibly track this progressive transformation from a simple organic sugar precursor right into complex carbonized structures. The biggest takeaway here is that turning up the heat and prolonging the time actively promotes the formation of carbonyl and hydroxyl functional groups. And this is exactly what leads to the development of those distinct graphitic domains.
Section 4. Optical properties, covering UV vis and PL.
So how does that structural carbonization affect the light? Well, the UV vis spectra show characteristic pi to pi star and n to pi star transitions at roughly 230 to 270 nanometers and 320 nanometers, respectively. Basically, as the synthesis conditions get more intense, we see increased absorbance and slight redshifts. This is a definitive, surefire indicator that aromatic domains are growing within the nanoparticles as they carbonize.
But hold on, because from an optoelectronics engineering perspective, we're about to hit the most critical and honestly exciting finding of the entire study: stable emission that is totally independent of the synthesis duration.
Our photoluminescence measurements brilliantly illustrate this highly stable blue-violet emission, peaking right in the 439 to 45 nanometer range when zapped with 355 nanometer excitation. What's truly remarkable here is how incredibly consistent it is. That blue-violet emission maintains its integrity almost perfectly, regardless of whether the synthesis lasted 12 hours or 64 hours. It is rock solid.
Section 5. STEM particle morphology.
To visually ground all that optical data, we turn to the physical morphology. These high-resolution STEM micrographs give us a fantastic, super-magnified look. They reveal these well-defined, quasi-spherical nanoparticles ranging anywhere from 5 to 60 nanometers. But they also reveal a key trade-off. Under the more severe hydrothermal conditions, meaning the higher temperatures and longer times, we start to clearly see particle growth and larger, agglomerated structures clustering together.
Section 6. Conclusions and applications.
To wrap up this academic explainer, let's look at the core implications. The findings conclusively demonstrate that hydrothermal parameters strongly influence the structural evolution of CLQDs while preserving consistent optical emission. In other words, the structure is highly tunable via temperature and time, but that crucial photoluminescence remains reliably stable. That makes this entirely green, sucrose, and water route extremely viable for sustainable device manufacturing.
So, I want to leave you with this thought as we continue the conference. As we perfect this green synthesis, how quickly can we actually scale these green, sucrose-based QCDs? What are the next immediate steps required to get them to replace traditional toxic phosphors in our commercial light-emitting displays? It is a real game changer. Thanks for joining us for this explainer.